In the previous example, you may be questioning, well, looking at this function, I could use the features of a quadratic function to figure out the maximum or minimum, right, of this function. But now I'm showing you why do we need to learn the first order conditions, okay? That is when the function form is not that straightforward to you, like this one. So it is 1/3 of x, one third of x cubed minus 4x squared plus 16x minus 29. And that's example 2 on page 5 of slides 5-1. Okay, so in this case, now it is a cube function, and we are not very sure about how this function curve will look like. So you can't just draw by hand easily the graph of this function and then analyze. So what we do now is we to rely on the two steps. One is to solve the first order condition, and the second is to use the second order condition to determine the relative extremum that we solved out, whether that is a minimum or maximum. So let's look at this one. First, step 1, we have to solve for the first order condition, the solution for this. Okay, so we need to first derive the first order derivative. That's what the first order is, right? First order condition. First order condition. Okay, so the first order means the first order derivative, and that is 1/3 of 3 times of x squared minus 4/2x plus 16. Okay, so now after 2 weeks, we should be pretty familiar with the derivative of the exponential functions, right? X cubed, its derivative 3 times of x, 3 minus 1, which is 2. That's the power, right? So now let's simplify this. We have x squared minus 8x plus 16. Okay, this is the function. This is the first order derivative. And we have to solve for the root of this first order derivative function. So the result is, so here it is actually x minus 4 squared equal to 0. The result is x equal to 4. Okay, so when x equal to 4, the f prime x is it's a relative this is a relative extremum, and now we need to determine the sign of it. So now step 2, second order condition. Okay, so f double prime x, what is that? Let's solve it out. So previously f prime x, we got this, which is x squared minus 8x plus 16. Then f double prime x is to take another order of derivative with respect to x. So it is 2x minus 8, right? The derivative of x squared is 2x. The derivative of minus 8x is minus 8. So when x equals to 4, f double prime x equals to 0. It's just equal to 0, right? When x is smaller than 4, f double prime x is smaller than 0. When x is greater than 4, f double prime x is greater than 0. So actually, this is just a relative extremum, and that is actually not a maximum or minimum. It's interesting. So why is that? Because here, if you take a second look, f prime x is x minus 4 squared equal to 0. When x is not equal to 4, this f prime x is greater than 0. That means for this function, when x is not 4, f prime x is greater than 0. Okay, so you can actually draw the functional form this way. So when x equal to 4, it is just a 0. When x is not equal to 4, f prime x is greater than 0. So the general shape is we're going this way, right? Fx increases in x. Then when x is smaller than 4, f double prime x is smaller than 0. What does that mean? F double prime x smaller than 0, that is concave function, right? So when x is smaller than 4, it is increasing, but increasing this way, right? When x is greater than 4, f double prime x is greater than 0, then it is convex. So you see the curvature actually changes around 4. This is what the function will be like. Therefore, it is a relative extremum, or we call this as a stationary point. It's as if previously we are increasing, but increasing in a decremental rate, right? Eventually around 4, the increasing rate is 0. That's why the first order derivative is 0. That is to say, the slope of the tangent line is just 0. The tangent line is just flat at x equal to 4. But when x is greater than 4, you start to increase in the growing velocity again, right? So here, x equal to 4 is only a stationary point. Since second order condition is not met, that is to say, we don't have a strict concave or a strict convex function around this point, right? In which it's like what I show you previously on the second page of the slide, right? Here, it requires that f double prime x is strictly smaller than 0, or f double prime x is strictly greater than 0 to ensure a maximum or a minimum. And here I'm using this example to demonstrate to you, even first order derivative equal to 0. That's why we need to check the second order derivative to make sure whatever you found as the stationary point, or namely relative extremum, is a maximum or a minimum. In this case, since second order condition is not met, x equal to 4 is merely a stationary point, not a maximum nor a minimum. So that's how we solve this problem. And I'm especially using this one first to refresh your memory and hopefully to deepen your understanding of how to graph utilizing the first order derivative and second order derivative, right? What is the functional trend told by the derivatives, and stress the importance of checking the second order condition to make sure the stationary point that you solve out is actually a maximum or a minimum.